In this demo, we're going to use cluster info to demonstrate how Kubernetes does auto-scaling. So before we start, let's go to Settings and make sure that neither mini or micropods are turned on and that Show Pod Resource option is selected, because we're going to use the resources inside the pod to determine how we need to scale that pod. So let's go ahead and create a simple deployment. So this deployment consists of 3 pods that are simply servicing web requests. And each request is a very heavy request, and each one requires some calculation. So each request is going to take some CPU resources. All right, now that Kubernetes has updated the resources that each pod uses, we can go ahead and see that at the beginning, each pod is using very minimal CPU resources. So now let's go ahead and put a small load on this on these servers. So we have another deployment, and all that deployment does, it sends HTTP messages at a very fast rate, and then as a result, these pods service those messages and perform computations with each request. So in a few seconds, we'll see the CPU values increase. Okay, now that Kubernetes has updated the CPU's values, we can tell that each of these pods is being taxed at their CPU level above its initial request value. So now let's go ahead and increase the load a little bit more. What we've done here is increase the load pods to 6 instances. So now there are 6 instances sending requests to the original workload. So now we're going to see the CPU values here increase even more and possibly approach or exceed the limit of each pod. So now that the system is stabilized, you can see that each pod is working really hard to service the requests that are coming in. So now let's go ahead and add a horizontal pod autoscalar to this deployment so we can see how Kubernetes can adjust the number of replicas to handle that demand. So within cluster info, the autoscalar is shown in the context of the deployment that it controls so that you could see how it's configured. And now that it's had a chance to look at the workloads, figured out the averages, its target average is 100 millicores, and it's figured out that the average across all the existing pods is over twice that. So what it's doing is it's increasing the number of replicas to try to handle that load. It's increasing the number of pods based on the scale-up policy of the pod autoscalar. So right now we have it set to 4 at a time. So at each iteration, it's going to only increase the number of pods by 4, and then going to wait until those pods have reported their CPU values, redo the average calculation, and then determine if it needs to increase it further. So now, after the previous 4 pods have started up and have reported their CPU values, it's determined that it's still above the CPU average, so that the number of pods has increased again. Even when the average value is adjusted, and even if that value is higher than the target value, the autoscaler isn't going to be able to do anything else because the maximum number of replicas is set to 12. So it's only going to be able to increase the number of replicas based on the up to the maximum. Okay, now it's recalculated the average again. It's much lower, but it's still above the target, so it's going to keep the current replica count as is. So now let's go ahead and lower the workload. Now we went ahead and lowered the workload down to just one load instance. So this should significantly reduce the number of requests that are coming in, and there are 12 pods to handle that request because there is a service load balancing those requests across those 12 pods. So the average CPU value should be quite a bit smaller the next time the metrics is updated. Okay, now we've seen the average CPU value has been reevaluated based on the decreased load, and that load spread across 12 pods. And now the system is going to decrease the number of active pods down to half as many. Now, it didn't make the decrease right away because it has a stabilization window, and that stabilization window says, wait for that decrease to exist for at least 30 seconds before taking any action. And having a stabilization window basically decreases thrashing of creating and deleting pods. So by default, that stabilization window is actually 5 minutes, but I've lowered it for this demo so that you could see it decrease considerably faster. But now it's decreased again. Another 30 seconds has passed. It's decreased the number of replicas again, and we'll continue to reevaluate the average CPU usage to determine if it needs to scale it down further. Now, when we started this demo, there were 3 replicas in the original deployment, but since the autoscaler is in charge of the deployment, the minimum number of replicas specified in this autoscaler is 2. Now it's in full control regardless of how many replicas were in the original deployment. Now notice that based on its reevaluation, the average was then again higher than the target average, and thus it had to increase the number of pods after decreasing them. And this is what I meant by having a large stabilization window to prevent this kind of thrashing from happening. Had it waited another couple of minutes, it would have seen the workload decrease and stabilize, and it would have kept it at a constant number. Now you could see the average CPU is below the target value. Again, the stabilization window has kicked in, so it's not lowering the number of replicas it needs just yet. It's waiting for it to stabilize. All right, now let's go ahead and remove the load from the system completely and wait for the autoscaler to adjust to determine that the CPU load is minimal, and then adjust down to the minimum number of replicas specified by the autoscaler. Okay, now it's been a few minutes. The workload has been removed, and now the metric server has adjusted and now displays the current workload. The autoscaler is waiting the stabilization period of 30 seconds before reducing the number of replicas down to its minimum. And again, that overwrites any original replica count that was in the original deployment. So this is how you can use cluster info to show how a horizontal pod autoscaler works within Kubernetes. In addition to CPU, you could also add memory as a metrics, and then the autoscaler will be able to scale based on either CPU or memory utilization independent of each other, and either resource value can trigger the autoscaler to increase the number of pods, and obviously both would have to be below the target value for the number of pods to decrease.